folks. How's it going? We are going to work on the in-class examples from 12.1. So I'm going to look for some volunteers and ask for some people to come up and write, do some work themselves. We'll talk about what they did or what was right or wrong with it. You may not get a choice. Like, I'll take some volunteers, but eventually probably run out of volunteers and you may just get picked on. So it's not personal. We're just trying to wring some participation out of you and like get both classes onto the same schedule or whatever. So, okay. Here we go. First problem says, suppose you have two fair dice, meaning all sides are equally likely to face up when rolled. The first die is four-sided with the numbers 2, 4, 6, and 8 on its faces. The second die is three-sided with the numbers 1, 3, and 3 on its faces. Let x be the number that appears on the first die. Write a probability distribution for the variable x. May I have a volunteer that feels like they can come and write the probability distribution? Sam, you're up. Can't put your hand on the screen and write at the same time.
Forgot what is it x equals x?
Yeah, that'd be perfect. Yep. If you go into Teams, you should see the class listed there. Okay, wonderful. And how do you know that's a probability distribution?
Because of having like each of the outcomes and the probabilities of that outcome.
Okay, so each of the probabilities is a valid probability between 0 and 1, and
they all add up to 1.
They all add up to 1. Those are the two things you need to check. Did you see the tile for our class? Okay. If you get stuck, I'm sure we'll show you what we did. Where do you grab? Part B says let y be the number that appears on the second die. Write the probability distribution for the variable y. Who wants to handle this one? Ella, come on down. Thanks. Okay. It is not.
Oh, okay.
That's okay. So let's talk about why it's not, right? Because that's a natural thing to try. What's wrong with what she's done here?
It would be like 2/3 probability to 3 because there's 2 columns.
Yeah, so y can only have one. Can't be 3 twice. It's either 1 or it's a 3. So should look like that. Very good, though. It's fine. Like, that's the point of doing this, right? Like, we haven't practiced yet. This is practicing. We're going to make mistakes, and that's okay. It's helpful even to have somebody come up and do what they would naturally want to do and have it be a mistake, and we can talk about why it's a mistake, and then everybody gets to learn before it matters if you make a mistake, right? Like, there's no problem making mistakes here. All right. C says, let event A be the total of the two dice when rolled together. Write a probability distribution for the variable A. So I'm not going to make one person do this all on their own because this is considerably more than the previous two. Why? Not because you have to do them both necessarily. So how many different values can A have? No. Okay. Can some of those outcomes occur more than one way? Yes. That's why this is going to be a whole lot more challenging, right? So to be able to calculate the probabilities to go into our probability distribution, we need to know how many ways, for example, I could get a 3 or a 7 or whatever, right? So what's going to be the best way to figure that out? A tree diagram. Yeah. Okay. So this first branching is going to represent the role of the dice X. What are the 4 different values that that first dice or die can come up with? 2, 4, 6, and 8. And the probability of rolling a 2 was, and the 4, and the 6, and the 8. Okay. Everybody's good so far? Now we'll roll the second dice. So there's only 2 different numbers the second die can come up with, right? 1 or 3. Everybody's okay? How many, or what's the probability of getting a 1? And 3? So if I look down this path, what is my sum of the dice then? 3. And the probability for getting that 3 or getting that particular combination on rolls would be 112. How did you get that, Marion?
It's multiplied by 4 times 1.
Because this is an and situation, right? We rolled a 2 and then we rolled a 1. The word and means multiplication. Okay. So far, so good. Now I'm just going to do the same thing for each path that I can take through this tree. So what is the sum of the dice for that path? 5, and the probability there would be 2 12s. Yeah, let's leave them all as 12s, because it'll be easier to check to make sure we have a probability distribution if they all have a common denominator. Is everybody good with that plan? Okay. Next path. That's a 5 also, and the probability there is 112. Okay. Next path. That's a 7. Okay. And the probability there is 12. this one, right? The one there. That is a 7. And the probability there would be 112. We have this one. It's a 9. And the probability there is 2 12s. We got 2 more. This one is a 9. And the probability there is 112. And then our last half is, 11. And the probability there is 2 12s. So if we go and we draw or write down our probability diagram or distribution, our different values that A can take are 3, 5, 7, 9, and 11, right? And the probability of getting a 3 is 112. Probably getting a 5 would be, okay, I can get a 5 this way, oops. Or this way, because we use the word or, that means add. 3 12s there, that's a criminal 3. And then for the 7, okay, and then the 9, and the 11. And does that all add up to 1? Yes. It's a lot more work than the previous ones, right? What made this much more difficult is that the outcomes can occur more than one way, and it was unclear just from looking at the sides of the die how many different ways those things were going to show up, right? Who wants to find the probability that A is greater than or equal to 5? Katie, get it. You're welcome. Wonderful.
Wait, so I said A, it says A equals A.
Yeah.
What's this like A?
That's some value of A is like is a set of these numbers.
Yeah.
Little a is a value in that set. That's usually just how we write up like a generic probability from a distribution. So it's like the capital letter is the random variable, and the lowercase letter is the value that random variable can take. Is that okay? So yeah, this is wonderful. What Katie did is she said, okay, well, this is P of A equals 5, or A equals 7, or A equals 9, or A equals 11, right? And because we said or, we add along those, right? Was there another way you could have done this? Anthony, what is it? You shook your head. I'm going to call on you now. Mary.
You could have just subtracted from 12. These are only 9.
Yeah, or you could have said this is 1 minus A is not greater than 5, right? Not greater than or equal to 5 means that it is less than 5. And in this case, the only number that A can take that's less than 5 is just 3. So you could have done it as a complement also. Either is fine. There's no advantage of doing one way or than the other. Right now, in the future, the complement may be considerably easier because you have to calculate less probabilities to do it sometimes. And as we get deeper in, calculating those probabilities might be rather difficult, even if you have a probability distribution. So if you can avoid having to do more number crunching, that's often helpful. Everybody feel okay? All right. So again, didn't matter which way you did it. This is obvious, right? What Katie did, I think, is the way that most of us would have approached doing that. And there's not much of an advantage of doing it as a complement because you have the whole probability distribution. You have to really compute anything extra. You had to add up more numbers instead of subtracting two numbers. But like, what you do that's adding numbers is not, adding 5 numbers is not much harder than subtracting 2 numbers. Not a big deal. All right. Example 2, it says the random variable z has the following probability distribution. Find the value of k. Who wants to take this one? Here. Yeah, get it. I have a feeling you'll do better than try. She's pretty good at school.
How do I erase?
You can just flip the pen over. It works just like a pencil where the back end is an eraser also.
Again, I'm not really sure where to go from there.
Okay. What kind of an equation is that?
Quadratic.
Perfect. So what are the different ways we have to solve a quadratic equation?
Factor.
Or what else can you do? Anybody else? To solve a quadratic?
Quadratic formula.
You could do the quadratic formula also. Who remembers the formula?
X equals negative b plus or minus squared b squared minus 4ac. 2.
You got it. Do that would be my suggestion. Now, why didn't we want to choose to factor this particular quadratic? What's making it difficult to do? Yeah, the leading coefficient isn't 1, which means you have to do that like long factor by grouping method, which is a little bit harder, and a lot of students forget how to do it because it comes up less frequently than the leading coefficient is 1, because as math teachers, we tend to use those more because they're faster and students are able to do that on a test. You do more test questions if you take less tedious stuff to do. Quadratic formula also has the added advantage of if our value for k was an irrational number, turned out to be like the square root of 2 or something, you can get that value out of the quadratic formula. You wouldn't be able to factor. Sure, you wouldn't be able to factor the quadratic that had a square root of 2 as a 0. Yeah, that's what I would do in this case, is quadratic formula.
Okay. Wait, can you have negative
Well,
as your k?
let's think for a moment. Can we have a negative value for k? No.
So here's 1/4.
Yes. Good. Can I ask a couple of follow-ups here while you're still?
Yeah.
Okay. How did you get this equation?
I added all the squared, like, so 3k squared plus 4k squared plus k squared, and then I got 8k squared. And then I did k plus k is 2k, and then since it's all the probabilities equals 1.
Why did you know that the probabilities have to equal 1?
Because that's the rule. Yeah.
Because it told you it was a probability distribution. If it didn't have that phrase, you could not do what you did. Just pointing that out there, that the directions told you it was a probability distribution was what allowed you to add up the probabilities and set it equal to 1. But that's correct. You did the right thing. And that's the right result. And Marin noticed that we got a negative value for k, which is fine if when we plug k back in, we don't get a negative probability. Right? But since we have these guys, plugging the negative into the squareds, no problem. Not wrong to do that. You'll get a positive value back out. Plugging the negative in for the linear term, that's the problem. Is everybody okay there? Now, we accepted 1/4 as our answer. We should do one other thing quickly to check, though. Because it's possible when I plug 1/4 in for k, I get a number bigger than 1. Right? And that's not okay. In that case, we just say there's no solution. So let's just check that briefly. 1/4 in for k, that's between 0 and 1, that's fine. 1/4 in for 3k squared, it's 3/16, that's fine. Okay, again, that's fine. 4k squared is 4/16, that's fine. 1/16, that's fine. Should feel pretty good. So just pointing out that, again, Marin did everything that you're supposed to do, did it the right way, did it the easiest way. That's great. I'm just talking through why we were able to set up the equation. And you should make sure at the end that you checked to make sure that the value for k is valid. Now, I don't think that, I wouldn't give you a problem where you solve for k and it gives you, an impossible problem. It doesn't work for a probability distribution. And I don't think the IB would do that either. But there's nothing inherent about, if I just wrote a random problem down, the k would not necessarily make it a valid probability distribution. If we just solve any quadratic equation. You get what I'm saying, guys? So just talking about, best practices or whatever. All right. Let's look at example 3. It says the random variable q has the following probability distribution, yada, yada, yada. In addition, 4 times the probability q is less than or equal to 1 is equal to 5 times the probability that q is equal to 3. And we're asked to find the values of both a and b. Okay. So we're going to need some equations to solve here to find the values for a and b, right? What's one equation that I can write that has a and b in it? Anthony. Yes. Why can I add them all up and set it equal to 1? It tells me it's a probability distribution, right? Again, that piece of direction, very important. So I can add up all of the probabilities and set it equal to 1. And when I combine my like terms, I have 6a plus 2b is equal to 1. Can I solve a one equation with two different variables in it? No. What am I going to need? A second equation with those same A and B, so I can make a system and use like substitution or elimination or something, right? Okay? Where am I going to get that second equation from? Yeah, perfect, Quinn. So what does this equation allow me to write? Good. Everybody okay with that? So the probability that Q is less than or equal to 1, so Q could be 1 or 0, so 4A plus A, because or means add, and then probability that Q is equal to 3, well that's just 2B, so that's going to be 20A or equals 10B, or just 2A is equal to B. Is everybody good with that? Okay. Substitution or elimination, which is going to be the more convenient option here? Substitution for sure, right? Because we're going to take this 2A and plug it into that B. Everybody's good? That eliminates a variable. So we're going to have 6A plus 2 times 2A is equal to 1. Or just A is equal to 1/10. Right? 6A plus 4A is 10A, by both sides by 10. And if B is equal to 2A, and B is 2/10, or 1/5, right? Everybody feel good? Let's just check here real quick to make sure that we're going to get valid probabilities out of this. So I have 4/10, 1/10, 1/10, and then 4/10. So those are all valid probabilities, and they add up to 1 still, so I'm positive I've done this correctly. Everybody feel good? All right. Questions on what we just did? It's okay. Again, the statistics piece, the probability piece, pretty easy, right? The hard part was realizing that, like, oh, I'm going to need to solve a system here, and remembering how to solve a system from way back in Algebra 2, probably. Everybody's good? Okay. The next one says, in example 1, find the expectation of A. So if we go back to example 1, here's our A. Who can compute the expectation for A? Marin, you want to go again? I love it. And you don't actually have to grind out whatever the number is there at the end. Like, that's good enough. Right. I don't have the calculator handy. I don't expect you to mental math that. Looks like Emerson's going to do it for us. What do we get, Emerson? Ah, punch those buttons faster. It's probably just that Marin wrote so small. You got that tiny, neat handwriting, so you get away with it. What'd we get, Quinn?
Might not be right.
88 over 12? I have, I think I printed out the 7.33. That could be 88 over 12, though. Maren says that's the same thing. Great. All right. Who can do the expectation for Z? Other than Maren. I think she's fulfilled her quota of volunteering. Right? Same thing as what Maren just did. So it's the values of Z times the probability summed for all values of Z. Anthony's going to do it since he's right here. That's what you get for blowing your nose. So Z, the probability for Z is here. 1/4 was the value for K that we found.
Plus, like,
So it's
parentheses
this
on
times
one.
this, and then plus this times this.
Oh.
Right? We're just doing,
Yeah, I
Not the same.
you got it. Well, put in the value for K, right? Make your life easier.
Oh my gosh.
Or Emerson's life easier, who's going to punch in the calculator for you, because she's already got it out ready.
Is that right?
Yeah, looks good.
Oh my gosh.
3/16.
Wait, please.
Correct. K is 1/4. Four sixteenths. I mean, you could write it as 1/4. I'm going to just make it simple so it's easy to see where we got it.
Yeah, I got 2.
Is that right?
Yeah, 2.44 is rounded to 3 sig figs is the correct answer. 2.44. Thanks, Anthony. And then the last part was expectation for Q. Emerson, get it. Bring that calc with you, too. Okay, best friend? You're dropping food off your sweater, though. What a slob.
Name.
Just scoot it over with your finger. Yep. So you can scoot it over, like it'll slide forever. You know what I mean? You can turn the pencil over and use it like an eraser. Yeah, I know, right? It's pretty slick. It's 1.5.
Oh, it's 1.5?
Yep. 1/10 plus 2/10 plus 12 tenths is 15 tenths. So 1.5. You're welcome, dude. Thank you. Is everybody okay? Feel good? We can do expectation. It's pretty easy once you've gotten the hang of it. Like, do it once or twice. The formula looks bad. It's not in practice. All right. You buy $10 worth of raffle tickets. You can place them in various drawings worth $20, $50, $200, $500, and $1,000. Let T be the random variable which represent the amount won on each ticket. This should really be like you buy really is like a $10 raffle ticket. It's really what we mean here. Let T be the random variable which represents the amount won on each ticket. T has the probability distribution given in the table below. Determine the probability that T is equal to $0. Who wants to handle this one? Anthony is volunteering Tomasino. What do you say to that, Tomasino? Yeah. All right, let's do it. I love that. Just remember this, Anthony. You volunteered him, he might volunteer you back. So we're just doing part A.
So you start by. I have all these up to give.
Wait, is the next worksheet gonna be harder than this one?
Kind of. So the key here, is that the probability distribution. So what do we know about the sum of these probabilities? That's the key.
So just add these up.
Yeah, so this is like X.
Okay.
Right.
Do I have to write
You can just kind of set it up and we'll write down the answer after. Or Emerson will punch into her calculator and get us the answer. I think Ella's already got it ready. So once you write out the equation or whatever, Ella will tell you the solution.
If I did it correctly.
Assuming she did it correctly, which.
what we got?
0.78.
Okay. So, here. So you guys, you wrote down it. So Ella has, so we want to write, you want to write this.
Oh, I see the next.
And then X equals 0.781. Is that what you said? Yeah, that looks good. Okay. Part B says, determine the expected value of T and interpret that meaning. Expectation for T, who's got it?
Oh.
Mia?
No.
Ella just volunteered you.
Give me the document.
Here, just write out. Ella will type it in the calculator for you.
You can do it.
You just write out what you want her to type in and she'll handle it for you.
Is it not? T equals 0. Is it not 0? Wait,
Looks good. So far, so good. Keep going.
Got
it.
Keep going. Wait, there's more? Oh, what is it? Oh, wait.
So plus.
Plus? Oh!
Yeah, you know how to.
All of it.
Yeah, all of it.
You got it.
Because all of that is the problem. There's the distribution for T.
That's also. Or no.
Thanks, Mia. Now I'm going to ask you, what does that mean? So we got 9.8 as a number. What does that mean?
It's the expectations.
Mm-hmm.
It's the expectation that we get. I don't know.
Okay, what does T represent?
Or money, yeah. Value. The amount won on each ticket.
So the expectation of T would be,
The average amount.
You got it.
No, I already forgot.
You got it. The average.
The average number of the average amount of one on each ticket.
yes, that's good. You stumbled your way to it, but that sounds pretty good. Right. On average, one ticket should win you $9.80. How much should you expect to win or lose when you buy that $10 ticket? Is it win or lose? Lose.
So you buy $10.
Yeah. Wait, why are you losing?
Because you spent more than you're gonna win,
Yes,
right? We expect to get 9.8 back, but we spent $10 to win it. So we lost 20 cents. Is everybody okay? So if you go and you do this expected value calculation for any casino game, you're always going to get a negative difference. It's going to cost more than the expected value to win. That's why casinos never go out of business unless they're run by Donald Trump. Managed to bankrupt a casino. Yep. I don't know. So you look at slot machines, roulette, blackjack. All of these games are built to have a negative, difference between the cost to play and the expected value, as are the lotteries, as are, like sports gambling. Like you're not beating anybody playing these games. All of these institutions have teams of PhD mathematics and computer science people working on ways to squeeze a little bit more of your money out by finding a way to obfuscate the negative expected return from playing. And sports gambling is probably the worst because it's a little bit harder to set odds appropriately. And if you're doing a good job and you're making bets where the odds are consistently shifting in your favor, like you place a bet early and the odds in the market shift to where you got a really good deal. If you do this consistently, what the sports gambling organizations do? They ban you, or at least they're certainly going to reduce the amount that you bet till essentially you can't win real money from them anymore. It's where it's you bet $10. That's all we'll let you bet if you're good at this. We don't want your business. We only want the stupid business. And then we'll try to incentivize you to bet as much as we can when you're making stupid bets. Even if you're managing to win money, we don't care about the wins and losses. We care about you gaming our system and making intelligent wins and losses. Because we know even if you're winning now, if you're doing stupid things, you're going to give us all that money back if we keep you playing. So we'll keep throwing free gambling at you to keep you coming back because we know we're going to get all that money back. Same thing at the casino, where they'll give you free nights at the hotel, because they know that you'll come back the next day and give back all that money that you won the previous night. They know that the longer you're there, the more you will lose, even if you've been winning big. In the 90s, a team of like Harvard professors worked out a strategy in blackjack to where you can actually find a situation where you have a positive expected value return for playing. And they got together some investors, and they put together a team of like students, grad school students and undergrad students, and taught them the strategy and funded them to go out and play, to play blackjack using this strategy. And, they won a bunch of money until the casinos caught on to what was going on, and then all these people got big. But essentially what would happen, what the strategy was, is if the deck, like when you play blackjack at the casino, they have like 10 decks of cards shuffled together. But while you're playing, eventually there becomes this point where the number of face cards that have the value 10 or more, if the deck gets heavy, if it gets above a certain percentage of the deck becomes those face cards, it's now the expected value of playing becomes positive. So the idea would be you play like minimum bets while you're in your head keeping track of how many of these face cards have come up and how many cards are left in the deck. And if it gets to a certain point where like there's enough face cards left, now you just start betting max at the table. And when the expected value from your bets becomes positive, now we bet as much as we can for as long as we can until the number of face cards dips below and we return to minimum betting, waiting. And usually I think that what they did was they had one person sit at the table and do the minimum betting the whole time and signal another person to come in when the deck got heavy that would do the max betting so it didn't look as suspicious. But that's an example of like looking, like that's how well constructed most of these casino games are. That like the instance to where you can get some positive return is complicated at best to get there, and really can only exist in like the card games. Can't happen in roulette or craps or anything because the amount of cards left in it, you have a conditional probability as opposed to an unconditional probability. Now, if you electronically do blackjack, it's impossible to do this. So if it's an electronic deck where you just have like every time you have a full deck of cards, there's no way to work that same advantage. That's why you're a sucker if you're playing like online gambling. Because even then, like you don't know what's in the code. The casino could go and do something like reduce the number of aces, so there's like 3.5 aces in the deck instead of 4. Because that's where the biggest payout in blackjack comes. Yeah. So like again, you can put your thumb on the scale, so to speak, and like again reduce the reduce the odds of you winning or increase the expected return for the casino. So my suggestion to you, if you were ever interested in gambling, do nothing electronically. The best odds in reality at the casino is playing poker, because you're not playing against the casino anymore. You're playing against other people. That's where you're gonna have the best odds of winning, because now it's turned into a skill game rather than, or at least some aspect of skill involved, rather than basically just straight odds. And the casino's not incentivized to take all your money. In fact, what they want you to do is keep playing as long as possible. And you win, that's fine. You lose, that's fine. But stay at the table, because the way the casino makes money from poker, they just take a percentage out of every pot. So every time somebody wins some money at the casino, they just pull 5% off the pot. It doesn't matter who wins or loses because it's not our money. We're just taking a percentage for facilitating the game. So that's the fairest game you can run into, unless you run into a group of people working together to play against you, which also happens. Instances where people have created teams of poker players that are there to just fleece the other people coming into the casino. That they just kind of work together and signal each other as to like what cards they have so they can create some edge in terms of making, your bets probabilistically. So yeah, that was fun, right? Little real world probability talk on where this can come into. It's a million degrees in this room. So again, like if you are playing poker, one of the strategies people will make as a novice poker player is you start learning to calculate, the percentage of your of like making your hand with the cards that are remaining or the cards that are out there. And one of the first things you'll try to do is figure out the expected value of your hand. So it's like you look at how much money is in the pot and the odds that you'll end up with the winning hand. And if the amount you have to bet to stay in the hand is less than the expected return you get from betting, even if you don't, even if you're losing, the smart play is to like, okay, I'm going to take this, I'm going to call this, even though I don't think I'm going to win. I don't have my hand, I'm going fishing. But the odds of me hitting times the amount of money in the pot for what I have to bet to play this hand gives me a positive return. It's like this lottery question where, you got to pay $9 for the lottery ticket and the expected return is $9.80. You should play that game as much as you possibly can, because even though you might lose in the short run, over the long run, you're going to be making a lot of money. So it's the same idea, like a game like poker, where you're playing against another person. If you can make bets that have positive expected value, where the amount you win times the probability of you winning exceeds the cost to play, then you should keep playing, even if you don't think you're going to win. Or even if the odds of you winning are small, like if you have a 10% chance, but it's like $1 million pot, it costs $1 to play, it's like, yes, please, sign me up for that as much as I can. Anyway, I don't know, I'm just kind of stalling now talking about stuff because I don't want to go and start the next section. Is this interesting at all? Yeah? Okay. I don't know, I feel like the sports gambling presence and the online gambling presence is so big, at least that's something that you hear about, occupy some bandwidth, might get your attention, about how kind of a bad idea it is in most cases. And if you are like gambling on sports and you're not thinking about things as what do I think the odds of this team winning are and what's the expected return from this bet, like if you're not thinking in that way, you're not doing it correctly. Like you need to start thinking about things probabilistically and placing bets that you think will have positive expected value. But the casinos are also, or these gambling companies are thinking the same way and trying to price these things in such a way that the positive expected value bet is not the bet that most people will place. Because for the most part, you probably want to be on the other side of what everybody else is doing. Because most people are dumb and not, betting things for the wrong reasons. Yes, sir. Sure. Anyways, I don't know. I feel like I've run out of stuff to talk about. So I'm just going to stop the recording. We can just relax for 15, 20 minutes or whatever.